Hello, Coach Travis here, coming at you with another calculus video. All right, this is a fun one. This is a problem basically from physics. So we got a car that's cruising along at 80 feet per second, and then I guess the driver presses the brakes, and the car decelerates, and we know that because of the brakes on the car decelerates at 16 feet per second squared, but just pressing the brakes, that's no fun. Let's pretend that the car is driving through a huge wall of jello. So all right, so the car is going 80 feet per second, and it hits the jello, and the jello decelerates it at 16 feet per second squared. And we want to know how many feet into the jello is the car going to travel. So how much of that jello is the car going to take out as it plows through the huge mountain of jello? And let's make it lime flavored jello. So anyway, how do we do this problem here? So this ultimately comes from antiderivatives. Okay, but again, like I always tell you folks, don't think about what you should do. Just kind of think about, well, what can you do? So I read this problem and I think, well, what can I do? Can I do anything? What can I do with this problem? And okay, well, when I read this problem, it tells me I know the deceleration. I know the rate of deceleration. So I'm going to write that as a function. So I'm going to say I know the acceleration function. The acceleration is a function of t. Ooh, and what's t? I'm going to say, because whenever you use a variable, you need to be clear on what that variable represents. So a is a variable, and a represents the acceleration of the car. And then what's t? Well, t is going to represent time, but I want to be even more specific. That t is equal to the number of seconds. So t is equal to the number of seconds, after the car hits the jello, after car begins the deceleration. It's the number of seconds. T is the number of seconds that the car is decelerating for. If I'm visualizing the car running into jello, the T is the number of seconds after the car initially hits the wall of jello. And okay, so then what's that function equal to? The function is equal to -16. And if I were you, I'd say, whoa, wait a minute, Travis, where'd that come from? And so first question I might have is, why is it negative? And well, it's because it's decelerating. So the speed is decreasing, so I feel like it ought to be a negative number. And then the other question you might have is, you might say, well, wait, where's the t? If acceleration is a function of t, then shouldn't there be a t over here somewhere? And the answer is no, because the assumption here is that the deceleration is a constant. It just says the deceleration is always 16 feet per second. So our deceleration shouldn't actually depend upon the time. It's always going to be -16. If there were a t over here, then as t changed, the acceleration would change. But that's not what's happening. What's happening is the deceleration is a constant. So there should be no t there. All right. So then what am I going to do with that? Well, so now what I do is I remember that, wait a minute, there is a relationship I guess let's go back. And what am I interested in? How many feet does the car travel before it stops? So, so that's a question about position. That is a question about position. And so this is a position question. And so I'm stuck here at acceleration. So I know about acceleration, but I want position. So I have to think, well, how can I get from acceleration to position? And well, hopefully you remember from physics or from calculus that, well, if you start with position and then you find the derivative, then you get the velocity. Now maybe I should write, so you get velocity. And if you take the, so let me see here. So let me write down. So there's position, so S is representing position. Maybe I'll put an arrow here. So S is position, and V is velocity, and A is acceleration. So from physics or calculus, I hope you remember that if I start with position and I find the derivative, then I get velocity. And if I have velocity and I find the derivative, I get acceleration. And that makes sense because derivative is the rate of change. And the rate of change of position we call velocity. And the rate of change of velocity we call acceleration. So that's doing derivatives. But I want to go backwards. So I want to go the other direction. And so that means what I need to use are antiderivatives. So if I find the antiderivative of acceleration, then I'll get velocity. And if I find the antiderivative of velocity, I'll get position. So I think I can use antiderivatives to get my position, because position is ultimately what I want. So, okay, so let's see. So antiderivative of negative 16 is going to be negative 16t, because t is the independent variable, and the antiderivative of a constant is just the constant times t. Oh, but then whenever you find an antiderivative, you have that annoying plus c that you have to worry about. But let's think for a moment. I bet if we're sneaky, we could actually figure out the value of c, because the problem gives me additional information. And whenever the problem gives you additional information, then that improves your chances of finding an actual value for c. So I look at the problem. What other information did the problem give me? The other information that the problem gave me was that the car was initially traveling at 80 feet per second. So let me think about what that means. So like this is how fast the car was going at time 0. So I could say at t is equal to 0, at the moment when the car hit the jello, the velocity was 80. That's velocity. Sorry for abbreviating. The velocity was 80. Okay, so if I write that in terms of symbols, I could say v of 0 is equal to 80, because v was our velocity function, and if we put time 0 into the velocity function, then we need to get the velocity at time 0, which the problem tells me was 80. But now let's use this formula. So if I put 0 into this formula, so v of 0 is equal to negative 16 times 0 plus c, right? If I just use this formula right here, and I put 0 in for t, then this is what I get. And so it's easy to see that those go away and you just have c. And so that means c is equal to 80. So this little bit of extra information that the problem gave me at the beginning allows me to say that that unknown constant is actually known. We actually know that it's 80. Oh yeah, and here's a pro tip. That whenever you do these antiderivatives and you get the plus c, the plus c is always your initial condition. It's always what is happening when t is equal to 0. So like in this problem, the velocity at time 0 was 80. And so that's why this had to turn out to be an 80. And we'll see that again here with the position. So let's do, well, I guess it's a little bit different, but it's basically the same. So let's do an antiderivative of this again to get position. So I'm going to get negative 8 times t. Actually, wait a minute. What am I doing? Give me a minute here. I think I'm working too hard. I got to think about this for a minute. Okay, I'm back. I thought about it. We're doing fine. I don't know what I was worried about. We're doing fine. So, all right. So back to here. I stopped right in the middle of a computation. I'm sorry about that. So the antiderivative of negative 16t plus 80 is negative 8t squared plus 80t plus, again, that annoying constant. Okay, but like we said before, the annoying constant is your initial condition. So since we're talking about position, the value of c should be our initial position. And the bad news is the problem doesn't tell us what the initial position is. So you might be, we're in trouble. But here's the thing, it actually turns out it doesn't matter what the initial position is. Because you can put any number just the way the problem's going to work out, you can put any number you want here. And you'll still get the same answer no matter what number you put here. And you'll see why when we do it. So the problem doesn't tell us what this initial position is. And so that at first is a cause for concern. It might be, oh my gosh, we're stuck. But it turns out that this number can be anything. Because all we really care about is what happens, what happens when the car starts to decelerate. So we don't really, it actually makes no difference where the car actually starts. So I'm going to go ahead and make this 0, just because since we can make it any number we want, we might as well make it 0. But just for fun, what you should do after we finish the problem is you should make this equal to your favorite number. So maybe your favorite number is 5. You should redo this problem and put a 5 there. And you'll see that you get exactly the same answer. So it really is, so you don't have to just trust me that it doesn't matter what number goes here. You can put any number you want here and you'll still get the same answer. Okay, so now where are we at here? Okay, so now I think we have everything we need. We've got the position function, so that's good because the question is ultimately about position. But I still feel like we're not out of the woods yet. How many feet does the car travel before it stops? Okay, so let me think here. Okay, so the distance the car is going to travel, the distance that the car is going to travel is going to be the position of where the car is when it stops. So I'll call that TS. So the S stands for stop. minus where the car was when it started, at time 0. So the car hit the Jell-O at time 0, and after a certain number of seconds, it's going to stop. And we want to find the distance traveled by the car is going to be the difference between those two positions. So, okay, so I can see the next step of the problem here, and that is I need to know how long it takes for the car to stop. How many if I could figure out how many seconds it's going to take for the car to stop, then I think I can finish the problem. But until I know how long it takes for the car to stop, I'm stuck. So all right, so pause the video for a minute and think about how you could figure out how long it's going to take for the car to stop. Okay, so I guess I'm assuming I don't have to pause because you're going to pause. So I'll go ahead and just tell you the answer. And well, when the car is stopped, that means the velocity is 0. So here's what I can say. I can say v of ts is equal to 0. Well, but wait a minute. If I use this formula, that's gonna be negative 16 times ts plus 80. Okay, so that means, so just look at this part of the equation. So again, what did I make? I want to make sure you understood what I did there because I went through it fast. So on one hand, ts is the time at which the velocity is 0. So v of ts has to be 0. Because that's what we're saying ts is. Ts is the time at which the velocity is 0. Okay, but now I need to use my velocity formula. If you put ts into the velocity formula, then you get negative 16 times ts plus 80. All right, so that now I can do some algebra here. And I can say, well, this is the same as saying 16 ts is equal to 80. So that means that ts is equal to, let's see, 8 goes into 16 twice, and it goes into that 10 times. Or what is that? 5? Oh, that's 5. That's just 5. Sorry. It's been a long day. So, all right. So ts is 5 seconds. So, all right, so what we've decided is it takes the car 5 seconds to stop. Okay, so now we can finish this problem. So we can say that, all right, the distance traveled by the car is going to be s of 5, because that's how many seconds the car is driving through the Jell-O, minus s of 0, and that's equal to, okay, so s of 5 is going to be negative 8 multiplied by 25 plus 80 times 5, and 80 times 5 is 400, and then we minus s of 0, but s of 0 is 0. And you can see this is why you could put in, remember the plus c? This is why you could put any plus c there. Because if you put plus 5, then there would be a plus 5 here, but then there'd be a plus 5 here, and there's a subtraction. So those 5s would end up canceling each other out. So that's why you really can have any starting position you want. Okay, and I accidentally erased part of my 8. All right, and then so this is whatever it turns out to be. 8 times 25, that's 200. So all right, so this is 200 right here. So all right, so the answer to the question is the car is going to plow 200 feet into the Jell-O before it comes to a complete stop.